Hello students, welcome to my YouTube channel. Today we are starting with our second unit, that is for the subject systems in mechanical engineering, introduction to thermal engineering. Now in this introduction to thermal engineering, we have thermodynamics, laws of thermodynamics, then we have heat transfer, then we have heat engine, that is the IC engine, and the steam turbine, steam generator, or the boilers. So we'll see this introduction to all this thermal engineering in this unit. So first we will start with our uh, first point, that is nothing but the thermodynamics. Now, what is meant by thermodynamics? What is meant by systems, or what are the systems in thermodynamics and all that? So if you see the definition of thermodynamics, so thermodynamics is a science of energy transfer. Thermodynamics, it is a science of energy transfer, and its effect, that is energy transfer effects on physical properties of the systems. So it deals with this thermodynamics. So it is the transfer of energy, and what are the effects of this transfer of energy in substances, that is the physical properties of that substances. So it is based on observations of common experience which have been formulated into a laws. So that laws is called as thermodynamics laws, and these all laws govern the principle of energy conversion. So the application of these thermodynamics laws or principles, they are found in all fields of energy technology. So notably, in case of steam and nuclear power plant, we have already seen this, how energy transfer can be takes place in steam power plant or thermal power plant and in nuclear power. Next, in IC engine, that is called as internal combustion engine. Then we have another applications of this uh, thermodynamics law, that is in gas turbines, then air conditionings, refrigerations, then we have compressors, pumps, where all their energy transfer takes place. So it is tells about this thermodynamics. Now in thermodynamic system, we have mainly first part, it is called as system. Second, it is surrounding. Third, it is boundary. And fourth is universe, which consists of all these three: system, surrounding, and boundary. Okay. So universe is that universe part. Now, what is meant by a thermodynamic system? So first we will see the what is meant by system. So system is a finite quantity of matter or finite quantity of mass. Matter is also called as a mass. Or a system is a prescribed region of space. So we have a region. In that region, we have take a small part. So that part is known as system. So system is a finite quantity of matter or a prescribed region of space upon which the attention is concentrated in the analysis of a problem. So we'll do analysis of that system. Okay, so that is the definition of system. Now we have surrounding. So everything external to the system. So everything outside this system, it is called as surrounding, or it is also called as an environment. So everything outside this system part, it is called as a environment or a surrounding. And the boundary. So boundary, the system is separated from its surrounding by a boundary, by its system boundary. So this boundary, it is either fixed type of boundary or it may be moving. You can move this boundary or it may be a fixed type of boundary. And last part is nothing but the universe. So universe is nothing but the a system and its surrounding together comprise a universe. So universe is isolated system because it contains everything, and thus there is no exchange of energy within anything, because energy can neither be created nor be destroyed. It can be exchanged from one form, that is one system, to another system. Not all energy it is constant of universe. So universe में जितने भी energy है, वो constant है. So there is no energy flowing in the universe. So it is isolated system. Now we have a boundary. Now this boundary, it can be either real boundary or it can be a imaginary boundary. So it is not difficult to envisage a real boundary, but an example of imaginary boundary would be one which drawn among the system consisting of a fresh mixture is there, in which uh, this fresh mixture of air and fuel, it gets enter in the cylinder of IC engine together, and it will form uh, IC engine together with a remnants to the last cylinder, and after that it get exhaust from the process. So there will be a two boundary. It may be a real boundary. So as like a system where piston cylinder arrangement is there, here is the system, and this will be a cylinder, this will be a boundary. So this boundary is located by this. So this is the boundary of the system. Here this boundary, it is starting from or consisting fresh mixture about to enter. So from entering to the combustion. So that boundary, it is a imaginary boundary. Okay, and this boundary is a real boundary. So here actually combustion takes place here, that is inside the cylinder, this part. And imaginary boundary, you can extend this real boundary to when there is air fuel mixture comes and we have a combustions. So this is what is meant by thermodynamics. What are the thermodynamic system? That is what is meant by system, then what is meant by surrounding, what is meant by boundary, what is meant by the universe. Now we will see the different types of thermodynamic system. So if you see, there are mainly three types of thermodynamic system. First one is open, second one is closed system, and third one is isolated system. So there are diagrams, they are there in the open system. So open system, we have mass entering in the system, mass goes outside to the system. Similarly, energy is inside the system, energy goes outside the system. In closed system, only energy in is there and energy out is there. Mass in and mass out is not there. And in isolated, both energy as well as mass, it is not in nor out. So what is the definition of this open system? The type of system where both mass and heat, it is maybe we can say mass, heat, or energy. It can be a heat, it can be a energy. So heat is one type of energy. So the type of system where both mass and energy transfer takes place with the surrounding, that system is known as open system. In closed system, the type of system where only heat transfer, or we can say energy transfer, that can takes place from system to the surrounding, but there is no mass transfer. So here both mass as well as energy transfer is there. Here only energy or heat transfer is there, no mass transfer. And third one is isolated system. In this type of system, where neither heat transfer will be takes place nor mass transfer will takes place, or neither energy transfer will takes place nor mass transfer will takes place. So these are the three types of different thermodynamic system, that is open system, closed system, and isolated system. So if you see, in case of open system, the matter or mass, it can transfer, it can cross the boundary. So mass from this system is cross the boundary and it goes to the surrounding part. In closed system, the mass is fixed. It has a fixed mass. Here, mass is not fixed because it is transferred from one end to another. But in case of isolated system, both mass is also fixed and energy is also fixed. So example, if you see the example of open system, then closed system, and this isolated system. So if you see a boiled water in a open vessel, it is an example of, say, open system. Again, second example will be the earth. So if you see this boiled water, it is open vessel. So there is no closing lid will be there. Okay, so it is open. So we can say the heat transfer takes place with the surrounding, as well as mass transfer is also takes place with the surrounding. Now, if you see in second example in closed system, boiled water in a closed vessel. So we have vessel that is closed. So in this system, if you see, there is only energy transfer will takes place between inside to the outside. Okay, there is no mass transfer. Mass is constant inside this. Mass is fixed. Or in isolated system, if you see, the insulation system is there. Insulator is provided. So no energy transfer takes place. No water mass transfer takes place. So example of closed system is boiled water in a closed vessel, then helium filled balloons. Next one is example of isolated boiled water in a thermoflask. Again, copy thermoflask. So these are the example of isolated system. So we have seen these three types of system, that is open system, closed system, and isolated system. Now we have different laws of thermodynamics. So we'll see, first we will see zeroth law, and in this video we will see the first law and a third law also. In next video we are going to see the second law of thermodynamics. So we'll start with the zeroth law of thermodynamics. Okay. So the statement of this zeroth law of thermodynamics, it states that zeroth law of thermodynamics states that if two systems are each equal in temperature, or we can say they are in thermal equilibrium. Equal temperature means they are in thermal equilibrium. So if two systems are each equals in temperature to third, or we can say if two systems are in thermal equilibrium with third system, then they are in equal temperature to each other, or we can say they are in equal, they are in thermal equilibrium with each other. So for example, if these two systems are there, or this is first system, this is second system. So temperature Ta is for A system, Tb is for second system. And if these two systems are having equal temperature, that is Ta is equals to Tb. And similarly, we have second system and third system, in which temperature of Tb is equals to temperature of Tc, that is the temperature of third system. Then the zeroth law states that there will be a thermal equilibrium, or we can say temperature equals between first system, that is A system, and third system, that is the C system. Okay, so this is the statement of zeroth law of thermodynamics. Now we will see the another example of this zeroth law of thermodynamics. If you see, now consider a system 1 is there. So we have a system 1. This is the system 1. This is the system 2 and these are the system 3. Now we will consider the system 1 consists of mass of a gas that is enclosed in a rigid vessel which is fitted with the pressure gauge. Now if there is no change in pressure, when this system is brought in contact with system 2, this system is brought in contact with system 2, that is a block of iron. Okay, so this is the second system. Then there is no change in pressure, there is no change in temperature, means they are is in thermal equilibrium. This system 1 and system 2, they are in thermal equilibrium, means they are having equal temperature. So we are assume that they are having equal temperature and the system 1 and system 2 do not react with each other by chemically or electrically. So the experiment reveals that if system 1 is brought into contact with again system 3, again there is no change in properties, that is no change in temperature and no change in pressure between system 1 and system 3, then uh, the system 2 and 3, it must be in equilibrium. Okay, because the system 2 and 3, they are must be in equilibrium, that is there is no change in pressure or no change in temperature. So this is called as a zeroth law of thermodynamics. Now this law was uh, enunciated by R.H. Flower in the year of 1932, 31. Before this 1931, the first law of thermodynamics was discovered. And again, second law of thermodynamics is also existed in that time. Before 1931, both first law as well as second law already exist are there. So therefore, this law is designated as again zeroth law of thermodynamics, as it precedes the first law and second law to form a logical difference. Okay, so this is called as the zeroth law of thermodynamics. Now we have a first law of thermodynamics. So if you see this first law of thermodynamics, so in first law of thermodynamics, it is observed that when a system is made to undergo a complete cycle, so there is a complete cycle for any system, then the net work done is done by the system or net work done on the system. Okay, so it is observed that when system is made under any complete cycle, then the net work done, it is either done by the system or the net work done is on the system. So for example, now consider a cycle in which net work done is done by the system. Now in this case, the work done is done. Now since energy cannot be created, this mechanical energy, now net work done is nothing but the mechanical energy. So this mechanical energy must have been supplied from some source of energy. So this network done cannot be possible without supplying any energy. Now system has been returned to its initial state. Therefore, there is intrinsic energy. It is unchanged because there is no energy change will be there. Hence, the mechanical energy has not been provided by the system itself. Okay, so it is there because of there is some energy supplied or some source of energy will be there. So the only other energy involved in this cycle, that is nothing but the heat energy. So heat which was supplied and rejected in various process, and hence by the law of conservation of energy, there will be a net work done by the system is equals to the net heat supplied to the system. So जितना आप heat supplied करेंगे, so net heat supplied by the system is nothing but the net work done by that system. So for that we require a cyclic process. So this is called as a cyclic process. This is cyclic integration. That is, there should be complete one cycle. So what is the statement of this first law of thermodynamics? When a system undergoes a thermodynamic cycle, this cycle is very important. Then net heat supplied to the system from surrounding, it must be equal to net work done by that system. It should be equal to net work done by that system. So mathematically, we can say that cyclic integration of dq is nothing but the net heat supplied to the system from surrounding is equals to dw is nothing but the net work done by the system. Now, the first law of thermodynamics, it is cannot be proved analytically, but experimentally we can prove this evidence. That is, जितना भी आप heat supply करेंगे, which is equals to amount of net work done by that system. So, experimentally, evidence has repeatedly confirmed its validity. And since there is no phenomenon has been shown to contradict this law, that is, heat energy gets converted into a network. So because of this, the first law of thermodynamics, it is accepted by a law of nature. It is accepted as a law of nature. So it may be remarked that there is no restriction was imposed which is limited to application of first law of thermodynamics to the reversible energy transformation. Hence, this first law of thermodynamics, it is applied for a reversible as well as irreversible transformation. So for cyclic process as well as for non-cyclic process, we can use this first law of thermodynamics. Now for non-cyclic process, a more general formulation of this first law of thermodynamics is required. So for cyclic process, we have that is cyclic integration of dq is equals to cyclic integration of dw. But for non-cyclic process, we have to apply some more general formulation. And this is done by using this Joule's experiment. Okay. So we'll see the statement. Again, we can say that the heat and work, they are mutually convertible. Means we can convert heat into work or work into heat. We can convert heat into work or we can convert work into heat. But since energy can neither be created nor be destroyed, so total energy associated to this energy conversion, it remains constant. So jitni bhi energy, either it comes from heat to work or work to work, it should be constant. Or same, we can say that there is no machine that can produce energy without corresponding expenditure of energy. Means there is no machine that produces the work without corresponding expenditure of energy. So for example, if you have to produce the work, so for example, if you have to swing the fan, so for that we have to supply some energy. So if we have to produce the work from that fan, then there should be energy supply should be there. Either it may be electrical or anything. So we can say that it is not impossible to construct PPM of first kind, that is perpetual motion machine of first kind. Okay. So if you see the Joule's experiment, in that Joule's experiment, there is a container, closed container will be there. And in that closed container, we have water. And to measure the temperature of this water, there is a thermometer. Now, this closed container, it is an insulated type of container. Means no mass will be go outside, no energy will be go outside from this system to the surrounding. Then another inert which having a fan will be there. So the work done, it is supplied by a systems. So by putting weight to this pulley system, there is a rotation of this fan and that will steer the water. So we supply the work to this system and the temperature of water goes on increasing. So there is increase in water temperature, and this temperature we can say that the net work input supplied to this system is nothing but the temperature rise of the water. That is nothing but there is change in heat energy. So the work input to the paddle uh, wheel is measured by a fall of weight. So this how work input will be there. It is measured by means of fall of weight, while the corresponding temperature of liquid in the insulated thermometer is measured by a thermometer. In insulated container, it is measured by a thermometer. So it is already known to us from this experiment that heat transfer from experiment on heat transfer, the temperature can rise and also it produces by a heat transfer. So because of heat transfer, there will be a temperature rise, and this heat transfer is takes place because of we supplied the work. So the experiment shows that a definite quantity of work is always required to accomplish some temperature rise obtained with unit amount of heat. So regardless whether the transfer is in opposite direction to the identical state from which started, this above result, it leads to the interference that work and heat, they are having a different form. They are not having same form. They are having different form. And something we can say this work and heat, more generalized, we can it called as a energy. So work is also a energy and heat is also a energy. So we can say that from this first law of thermodynamics, it can be stated that for it can be stated as the invariable experience that whenever a physical system passes through a complete cycle, the algebraic sum of work transfer, that is algebraic sum of or cyclic integration of work transfer or dw during the cycle bears a definite ratio to the algebraic sum of heat transfer, and that ratio is called as J. So we can say J is nothing but the cyclic integration of dw upon cyclic integration of dq. So that is nothing but the J. So this J is called as proportionality constant, and it is known as mechanical equivalent heat, and its SI unit is this SI unit is a Newton meter per joule. It is the proportionality constant, and its value is unity 1. So this is the first law of thermodynamics. Now we have third law of thermodynamics. So we'll see second law of thermodynamics in next video, where we have heat engine, heat pump, and refrigerator there. So we'll have a third law of thermodynamics. So statement is that so entropy of all perfect crystal solid for crystalline solids is zero. So entropy is zero for all crystalline solids at absolute zero temperature. Now this is very much important. So entropy is zero for all crystalline solids, but it is at absolute zero temperature only. So if you see the entropy, yes, is zero when the temperature T is equals to zero. And if temperature is greater than 0 Kelvin, the entropy is again greater than 0. Okay. So a perfect crystal where entropy is 0 when there is the absolute temperature is 0. So third law of thermodynamics is often referred to as Nernst's law, which provides the basis for calculation of the absolute entropies of the substance. So however, at this temperature above absolute zero, the entropy is a function of pressure also. So above this absolute zero temperature, the entropy is a function of pressure. So pressure changes, the entropy will also get changes. The absolute entropy of a substance at atmospheric pressure, that is at 1 atmospheric pressure, can be calculated by using equation. So for pressure difference from 1 atmosphere, so it is nothing but the pressure difference between the 1 atmospheric pressure at 1 atmosphere. So therefore, the necessary correction have been applied. Now, limitation of this third law of thermodynamics is that the mixture of isotopes, do not show zero entropy at absolute zero temperature also. So for we require only perfect crystallized solid. If there is a mixture of isotope will be there, then that will not show zero entropy. Again, the gaseous solids such as carbon monoxide, carbon dioxide, nitrogen oxide, then nitrogen dioxide, NO2, then H2O. This does not show again zero entropy at the absolute zero temperature. So for that we require the perfect crystalline solid other than this mixture of isotope and glassy solid. So this is all about the laws of thermodynamics. So in this video, we have seen the zeroth law of thermodynamics, first law of thermodynamics, third law of thermodynamics, and what is meant by thermodynamics, what are the thermodynamic system in which we have a system surrounding universe boundary and different types of thermodynamic system, that may be open system, closed system, and isolated system. So this is all about this video. So thank you for watching this video. Also, subscribe my channel or to get the updated videos based on this second unit, that is introduction to thermal engineering. So thank you for listening my video. Thank you very much.